Well, hi guys. You'll have to forgive me. I'm a little bit under the weather. Kind of like hurt my back. I'm kind of behind in school stuff at the moment, but I'll try. Hopefully it's not too obvious. So anyway, last time we were talking about Stokes Theorem. So this is what we did last time, which is Stokes Theorem. Can you all read it in the back? Can you see it? The hardest part about Stokes' theorem is figuring out what the heck the boundary of a surface is. So we started off with Stokes' theorem for graphs, which is what I did up here. It's what we did last time. And I'm going to do an example using this theorem. And then I'm going to give you the more general form of Stokes' theorem, which applies to general parametrized surfaces. Let me remind you what the boundary of a surface is, which is, I used this piece of paper as an example last time. So let's say like this is a surface just floating in 3 space. The boundary of this surface I tried to indicate in blue. I also gave it an orientation where the orientation is the path that goes around the outside of the surface counterclockwise. Well, it's counterclockwise if you look at it from this side. What if I looked at it from the back? Well, then it would be going the other direction. So how do you know which side are you supposed to be looking at the surface from? It's kind of arbitrary, actually. You just choose one, and you name that, or make a decision that that choice is the positive orientation of the surface. So if I tell you that the normal points towards you guys in this direction, here's a handy little rule to remember which direction you traverse the path. It's called the right-hand rule. Yeah, you hold out your right hand and you point your thumb in the direction of the normal vector. If your thumb is pointing in the direction of the normal vector, then your hands curl around in the direction that you would traverse the path in. Okay? So with my thumb pointing at you, you can see my hand curls in the counterclockwise direction. So with that being the setup, you can see right here is Stokes' theorem for graphs. Let's do an example. Here's my example. Let f be the function xy, comma z, comma 0. And S, my surface, is a triangle, but in 3 space. So let's place the vertices at 1, 0, 0, 0, 1, 0, and 0, 0, 1. And let's verify Stokes' theorem for this surface. All right, so try and draw it. Got a vertex here, here, and here. So there's S, my triangle. Now, S can be viewed as a graph. S can be viewed as the set of x, y, z, where z is a function of s and y, x and y. Z is 1 minus x minus y on that plane. For xy in D, where let me show you what D is. D is this triangle in the xy plane. So there's D. If we looked at D from above the xy plane, then that would be D. And the top boundary of D is the line where y is equal to 1 minus x. Any questions so far? Okay. So that means we can use the Stokes theorem for graphs formula. So let's see, let's find, I guess we'll need del cross f. Del cross f will be determinant I hat, j hat, k hat. And I'll just tell you that we get -1, 0, negative x. If I'm going to integrate the flux of that curl over the surface, I will need the normal to the surface. Since S can be parametrized as the set of x, y, z, where z is equal to 1 minus x minus y. In fact, sorry, let me write this a little bit differently. Crap, my surface is messing up. S can be parametrized as the set of x, y, and 1 minus x minus y for x, y in D. So I can find tangent vectors Tx as 1, 0, -1, and Ty as 0, 1, -1. So normal vector tx cross ty is equal to 1, 1, 1, as it so happens. Let me try and draw that. So that's like this guy. Okay, so now let's start doing the integral. The integral over S of del cross F dotted with ds is the integral over d of -1, 0, -x dotted with 1, 1, 1. That's the integral. Let's see, x goes from 0 to 1 in d, and y goes from 0 to 1 minus x in d. So at this point, the surface integral is pretty straightforward. So please let me know if anyone has any questions on this up to here. Okay, so that's 0 to 1. Let's see, that turns the integral of x squared minus 1 dx. It's x cubed over 3 minus x. So I get -2/3. But I'm supposed to verify Stokes' theorem, so I should also get -2/3 if I do the line integral. Okay, so let's do the line integral. The line integral around the boundary of S. What is the boundary of S? S looks like a triangle. So what's the boundary of this triangle? It's a yeah, okay, yeah. So S is the interior of the triangle. The boundary are the three edges. Which, what was the definition of boundary that I gave? It was you first, so let's go back a step. You look at the boundary of the underlying domain, and then it's the parametrization of that boundary, right? So it's like you look at these points on the boundary of your domain, and where do they get mapped to under the parametrization? In this case, here's our shape. The boundary of the underlying domain was these three sides. So they get mapped to, what's another good color? Gold. Okay, so they get mapped to this side, how about I'll call this C1. This side, I'll call this C2. And this side, I'll call that C3. Okay, so that's the boundary of the triangle, C1, C2, and C3. So in fact, let's see, if this is C1, and this is C2, and this is C3. So there's more than one way you could parametrize them. You kind of have some choice with how you want to do this at this part. Let me do C1 of t. How about I'll parameterize that as the set of 1 minus t, comma, 0 for t between 0 and 1. Does that work? And for side C2, I'll parameterize C2 of t as, let's see, I think x is 0. I'll do y is 1 minus t, and z is t for, again, t between 0 and 1. And then for, what's going on? What is, oh, is everyone getting calls telling them to vote? Is that what's going on? I got like 2 or 3 texts. Huh? Yeah, right. Okay, yeah. So C3 can be parameterized. Let's see. X is t, y is 0, z is 1 minus t. Again, so there's, as you learned from back when we did paths, there's more than one way that you can parameterize a path. I thought this was maybe the easiest way to do these 3 sides. So okay, let's do the, let's integrate over these 3 line segments, because the integral of f over the boundary of S will be the integral, of S over the bottom one, the first one, plus integral of f over the second one, and plus the integral of f ds over the third one. So let's do the first one, integral of f over C1. Is the integral, let's see, t went from 0 to 1 in C1. F, what was f? F of C1 of t is x times y. That's t times 1 minus t, 0, 0. Because remember what f is. F was, where was it? F was this function. So that turns into t1 minus t, comma 0, comma 0, dotted with c prime, which is negative 1, 1, 0. That's 0, 1, t squared minus t. So that's t cubed over 3 minus t squared over 2 from t equals 0 to 1. 1/3 minus 1/2 is negative 1/6. Okay. How about for the integral over C2? That will be 0 to 1. What's f of C2? X times y, that's 0. Z is t. So it's 0, t, 0, dotted with, let's see, C2 prime, negative 1, 1, 0, negative 1, 1. It's negative 1/2, okay. Finally, over C3, that is 0 to 1. F on C3, what is F on C3? X times Y is 0. Z is 1 minus T. 0, 1 minus T, 0. But what is C3 prime? 1, 0, negative 1. Nice. So I get 0. Sweet. So adding these three up, the path integral, or line integral rather, of ds around the boundary is, we got negative 1/6 minus 1/2 plus 0, which is negative 2/3. Same answer. Same answer as we got last time. Yeah. All right. Cool. So it's my big Stokes Theorem example. You see why I didn't want to rush it last time? We had 8.5 minutes at the end of class, and this was a 10-minute problem. Any questions? All right. Well, I guess I can try to explain Stokes' theorem for general parametrized surfaces now. So in order to do Stokes' theorem for general parametrized surfaces, we have a sticky issue, which is, it's pretty intuitive once you get the hang of it, but at this level, it will be lacking in rigor, okay? And I'm talking about the notion of the boundary of a parametrized surface. So how do you define that? Well, your book has a way that it defines it, but I don't like it. But I'll tell you what the book's is, and then I'll tell you my own way to define it as well. Before I do, let me just get your opinion. What's the boundary of the unit sphere? Do you think you know?
I'm going to guess it's like the minuscule point at the
Point at the ends. Interesting. Okay. Now, the sphere is very symmetric. Boundary, taken as a geometric concept, should be coordinate free. Like, it shouldn't depend on what earthly coordinate system you use to define your shape. The sphere, the most perfect of all shapes, exists independent of any coordinate system. How could you pick out as special any point or path on the sphere, since every point on the sphere looks just like any other? So the sphere shouldn't have a boundary. How could you even say any one point is any more or less special than any other? The sphere does not have a boundary, okay? As we shall see. But how to derive that rigorously? So keeping that in mind, let me ask you another question. What about the boundary of a half sphere? So consider the shape sine phi cos theta, sine phi sine theta, cos phi for let's say theta in 0 to pi and phi in 0 to pi. What should the boundary of this shape be? And second, I'll ask you to consider something very similar. Okay, so that first shape, see if I can draw it. So I gave the spherical coordinates of, well, it's all the points on a sphere, on the unit sphere for which the polar angle is between 0 and 180. So that is going to look like it's all the points from here up to here. On the other hand, the second example, that's just the northern hemisphere of a sphere. So that's all the points up here. Okay, so what should the boundary of those two shapes be? Well, how about for the question one, what's the shape of the boundary? It is a circle, yes, indeed. But so how did we know that? How could we figure that out? Similarly, for question two, the boundary is a circle. Let me tell you the book's definition of the boundary. So suppose that we have some parametrized surface and suppose the parametrization is 1-to-1. Freak. This tablet's messing up again. Then the boundary, then phi of the boundary of D is the boundary of S. That's what the book says. If you have a parametrization of the boundary of D, then P of t, which is equal to phi of U of t v of t parametrizes the boundary of S. So let's apply this definition to the two shapes that I was discussing above. In question 1, phi and theta live in R2, and they go from 0 to pi, and 0 to pi. So, like, where do these boundaries go to? How about this boundary, the one where phi is 0, theta goes from 0 to pi. If phi is 0, what shape is that? The green. Huh? A point. Good. Yes, that's just the North Pole. So under the parametrization, that whole line segment just gets mapped to a single point. Okay, how about this side, where phi is pi, sorry, theta is pi, and phi goes from 0 to pi. That's, okay, it might be hard to say in words. Okay, so let's see. That looks like it was going to go down back there, yeah. And let's see, if we go back the other direction right here, that's just going to correspond to this single point right there. And finally, if we go down right here, it's where phi goes back to 0, and theta is 0, so that goes back to there. So indeed, if you said a circle, you were correct. It's the boundary is that circle. Similarly, well, okay, let's see just how similar it is in the second question. So in the second question, phi and theta again are in the plane. Here's theta, here's phi. Let's see, theta goes from 0 to 2 pi. Phi goes from 0 to pi over 2. So how about, let's see, the bottom, when phi is 0, that's just the single point on top. When phi goes from 0 to 2 pi, and theta is 2 pi, let's see, that's going to go as such. When theta goes back to 0, oh, that's the interesting one. So theta goes backwards, so we're going to go around the circle, around the back of the circle. And then finally, when phi goes back down to 0, we go back up to the top. So is that boundary a circle? Kind of. Well, not part of it is. Part of it's not. It includes a circle. It's like a circle with a handle on it or something. But can we treat it like a circle for the purposes of Stokes' theorem? We can. Why? We have two paths that cancel each other out. Yeah, so like this, the red and green part here, one's going one way, the other's going back on top of itself. Those two line integrals are just going to cancel each other out. They're just going to be negatives of each other. It's as if we could just, cross them out. And what's left is really the boundary of this shape, which is this circle right there. Okay, so yeah, the key fact is if you use the book's definition, it's kind of weird, but some paths are going to cancel each other out. Personally, I have what I think is a more intuitive definition, which is just you can take surfaces and chop them up into graphs. And we already saw how to do boundaries of graphs, of surfaces that are graphs. And then when you piece them back together, just remember that some of the line integrals will cancel each other out in the manner that I just showed. That's another way you can think about it. FYI, for those of you that are interested, a differential geometer would have a much more rigorous definition of the boundary of a surface. It would be, and you're not going to know these terms, but don't worry about it. You would say that a boundary of a surface is the region that is diffeomorphic to the half plane, is what they would say. So that can be made quite rigorous, but it's beyond the scope of this class. Yeah, wait, what was Mosh? How do you say your name? Micah, yeah.
How does that boundary give us any meaningful information about what the surface is? Does that boundary can also be the boundary for just that circle or for the other half?
Indeed. Good point. Micah asks is like, well, couldn't multiple surfaces have the same boundary? That's exactly right. So that tells us something deep, actually, about Stokes' theorem, which is you can have entirely different surfaces, but as long as they have the same boundary, the flux of a C1 vector, of the curl of a C1 vector field through those surfaces will be the same. So I'll do an example of that. We'll get to that. Let me just state Stokes' theorem for parametrized surfaces now that I feel we've spent enough time on defining their boundaries. It's going to look a lot like the Stokes theorem we already saw. So, okay. There it goes. Let S be an oriented surface defined by a one-to-one parametrization phi where D is a region to which Green's theorem applies. You have to orient the boundary. Then the integral of the curl, the flux of the curl of f across S is the line integral of f around the boundary of S. A notable case is when the surface doesn't have a boundary. So, for example, a sphere, what would happen if there is no boundary to integrate over? It's 0, indeed. So if S has no boundary, okay, so here's an example. How about we let F equal y plus z squared negative x plus 2z and sine z. So I'm going to draw it in a second, but the problem will be to find the flux of the curl. So here's the picture. Okay, so the circle that it's sitting on top of is the unit circle in the xy plane. And the sphere, it's kind of like this. Okay, so there, that sphere is S. So S intersects the xy plane in the unit circle. I didn't even say where x was centered at exactly, because just like Mike was pointing out, you don't actually need to know details about S. It's sufficient to answer this question. We just need to use the path, the boundary of S, which is given by this path right there, which it's the unit circle in the xy plane. It's the set of x, y, 0, such that x squared plus y squared is 1. And oh, I didn't give an orientation to it yet. Let's just say like the outward pointing direction is n, which, what orientation does that induce on the boundary of S? Let's say if the axes are labeled in the usual way, like if this is x and this is y. So it induces the usual counterclockwise orientation of x and y. So that's the usual direction like this, according to the right-hand rule. All right, cool. So then let's do that. A parametrization of the boundary of S that is consistent with the orientation is cos t sine t 0 for t in 0 to 2 pi. Then the flux of the curl is, by Stokes theorem, the line integral of f dot ds. Sorry, yeah, yes, that is right. Sorry, f dot ds. Little s. So what is that? That's from 0 to 2 pi. F on the circle is sine t plus 0 squared negative cos t plus 2 times 0 sine of 0 dotted with negative sine t cos t 0. So that's 0 to 2 pi, negative sine squared t minus cos squared t dt, which is negative 2 pi. Any questions? Okay. Finally, how about this one? So I'm just going to, let's use the same path, the unit, still same unit circle in the xy plane. And let's use the same f as before. But for my surface, let's make it, I try to make it like a chef's hat. How about? So let's make it look like, is this what a chef's hat looks like? Got a big puff, 2 puffs, 1 puff, 2 puff. How about like that? Okay, so it's kind of like that. It's got a big poofy part up here. And let's give it the inward normal now. So chef's hat, but with the normal sticking into the chef's hat, what is, with the same f as before, what's the flux of the curl through this surface? Oh, okay, I see someone has an answer. How about Larissa? Wait, was it Larissa? Is there a relation between this problem and the last one? This problem and the last one both have the same, at least if I drew it decently, they're supposed to both have the same boundary of the surface. So, since according to Stokes theorem, we should get the same. It shouldn't the surfaces have the same boundary. Stokes theorem says we should get the same answer, right? At least if they are oriented the same way. Did I orient it the same way? Let's see. I stuck the normal vector into the hat. So if you stick, I had a hat and I stuck my hand in, and let's see. that would be, oh, oops. That has the opposite orientation. Oh, so now, according to that orientation, we go around it this way. So we should get the negative of the answer we got before. So we should just get positive 2 pi. Because we just go around that same path, but in reverse. Cool. Okay. Do a bit more on this next time.